$2.9 billion. This is the yearly cost of hospitalizations due to potassium level derangements. A big reason this cost is so high is due to patients' potassium levels slowly trending out of control at home. Just think of the ramifications of a diabetic patient not having a glucometer. The importance of diabetics measuring their glucose at home is widely known because patients who do not regularly check their glucose level are often hospitalized after becoming extremely sick following large deviations in their glucose. Now shifting back to potassium level derangements, it is surprising that there is not a similar way to measure one's potassium at home. There are almost 6 million American patients with either congestive heart failure or end-stage renal disease who are very prone to hypo or hyperkalemia, respectively. Hypokalemia, a condition with low potassium levels, increases the risk of sudden death, while patients with hyperkalemia, a condition with high potassium levels, often require emergent dialysis. That is 6 million patients who would greatly benefit from an at-home device that will allow them to catch potential potassium derangements and decrease the $2.9 billion spent on related hospitalizations each year. Due to the engineering problem, we have created a home device that will measure serum potassium levels within a 0.1 millimolar accuracy. Although there are currently devices that measure potassium in a lab setting, these take 30 minutes and require an IV-drawn blood sample to complete. And while there are devices attempting to gain FDA approval for home use, they are substantially inaccurate due to large interference from molecules such as bilirubin. Furthermore, these devices are relatively expensive, costing upwards of thousands of dollars. Our device will cost less than $200 and eventually seek FDA approval through creating an accurate at-home device by utilizing a gel electrophoresis to separate potassium from a patient-provided finger prick blood sample. The agarose gel will contain a krypton molecule which will fluoresce when bound to potassium. Moreover, the intensity of this fluorescence will correlate to a specific potassium concentration. Therefore, it will be possible to measure the potassium concentration by measuring the intensity of the emitted fluorescence. This miniature gel electrophoresis will be contained within disposable test cartridges, which will be inserted into a device which will provide a high voltage to run the gel electrophoresis and then will measure the fluorescence and output the potassium concentration to the user. We feel our team is best suited to solve this problem due to our diverse engineering skill set, extending from biomedical to electrical engineering, as well as our previous clinical experience working in the emergency department and shadowing physicians of multiple specialties. The next steps for our device will be to complete further testing to demonstrate the reproducibility of the potassium readings. After this initial testing, additional funding will be needed for FDA approval as we will still require clinical trials to verify that the design can be used accurately at home. However, once completed, we adamantly believe that this product will provide great benefit to CHF and end-stage renal disease patients by limiting illness and hospitalizations. This will in turn alleviate a great amount of cost to the healthcare system and provide a better quality of life for millions of patients.